Everybody, can you all hear me?
Yes.
Great. So this is a crash course on pgRouting. Let me introduce myself first. I am LEO HSU. My wife, the better half, the smarter half, is Regina Obey. She's actually on the PostGIS steering committee, and I'm not. So we'll see how this goes. We are writing a book on pgRouting, and this link will take you to where you can buy this book. Now, someone did ask me what the price would be. I don't know what the final price for the hardcover will be. It'll be similar to other locate press books. However, right now, if you buy it by the electronic version, right now, when we only have like half of it written, it's 50% off. So jump on board now, and then, yeah, and then we'll finish it. We'll finish it at some point. Okay, all right. So the important thing I want to do today is make sure that you have the basics of pgRouting. There are a lot of internal algorithms. We're not going to worry about that. I don't really understand all of the internal workings of it. But the idea is that you could go home tonight, grab some data, and start doing some routing. You can route your home from the optimal path from your front door to the bedroom, whatever. So I'm going to go real slow, and stop me if you have any questions, and we'll answer it when the slides, and actually I don't have any slides besides this one. Okay, so let me dive into it. Okay, so the first of all, routing in general term is something you find on a GPS of your car. There are many different variants of routing, but they all pretty much answer the same question, essentially how to get from point A to point B in the most optimal fashion. Okay, to use pgRouting, you need to have it installed, and people can see that, right? For Windows platform, it's very easy. There's an installer, but for the other Linux distributions, you may have different places where you download pgRouting, and then you have to compile it on your own. There are a lot of places that's also compiled it already for you. Once you have pgRouting, you have to make sure you enable this extension, and I have already done that in my workshop database here. You will see that I have the pgRouting extension. So before you do anything, you need to make sure that this is available to you, this routing extension is available to you, and the most current version is 2.2.2. 2.3 is coming out later. It's a lot of things that's been planned for it, but we do not have a definitive date yet. Okay. So let me start with some simple examples. And this is pgAdmin, which is the graphical tool that I like to use for interacting with PostgreSQL. I know a lot of people like to use that command line that's black and white. I can't. That's way too much typing and remembering syntax for me, so I like to use the graphical version. And remember, if your server is Linux, you can still install this graphical version on your own laptop and access it. Okay. So I have a script. Okay, the first example that I'm going to present is your very basic routing problem. let me clean up my table first so I can start fresh. Okay, this is some data that I downloaded from OpenFlight. It lists, and I pared it down to just the relevant information that we need. And essentially, you have a unique identifier. You have a from airport to airport. It reports the duration of the flight. And then from an airport's table, I was able to get the longitude and the latitude, the long lat of the two airports. There's a lot more information in this original data set, but I'm not going to worry about that right now. For example, you can find out what airline, what type of plane, and all that stuff. The only thing it doesn't have is fares, so it does not list current fares. Okay, so yeah, let me increase this. Oop.
I also wonder if your SQL window
Okay. Hold on. Let me. Yeah. Okay. Let me move. Do you want the SQL on top?
You just drop the mic here because we're all happy.
All right. Okay. I'm going to keep the SQL at the bottom because it's, if you have a problem with that, let me know. Because I'm used to it at the bottom and I want to highlight the data. Okay, so now we have to scroll to see the data. So this is what we're going to start off with. Okay. The first thing we have to do is, well, we have all the points. So these are all the airports around the country. Routing is based on edges, which is also known as the segment between the points, or also known as the nodes. So I'm going to derive those segments by creating a line string. So I'm going to first add a geometry column. Okay, and that is simply a line string. And I'm constraining that line string to be 4326, which is your regular longitude, latitude, WGS 84, 83, the very popular one. Okay, and then I'm going to make a line, and I'm going to make a line that connects. Where's my scrolly thing? Okay, wait. Okay, so here I am going to make a line from my airport of origin to my airport of destination. So let me do that. Okay, so now I have 4,953 segments that will interconnect most of the airports, or at least all the airports that I want to consider. Yes, there were some airports that's off in the Bahamas, but we don't want to worry about that. Okay, and I will show you all this in a picture soon. Now, to prep the data further, we need two columns. These are absolutely essential, and they need to be named as such. You need to add a source and a target column. And I am just adding that right now. Okay, so let's look at our flight table right now. Okay, so we have our original airports. We have our duration. And at the end, I tagged on a line string which connects the two airports. And then I added a source and target column, which are both null at this point. Now comes a very magical, and a very, very powerful function that you need to know. So create topology will basically take what I have told it in terms of points, in terms of edges, and it will create a network for me. And what I mean a network is when you do routing, you're really looking at a path that is well structured, so there's no dead ends, there's no points that's out somewhere that you can't get to. So it has to be somewhat well behaved. And when it's well behaved like that, I call it a network. So it has to be properly noded. That's another term. And you'll see here, to use this function, I can specify a tolerance. And this is 0.001 the tolerance is specified in the measurement of the spatial reference system. In this case, longitude, latitude, so 0.001 degrees, if you will. And that is the tolerance. And what this tolerance does is magical. If you have edges that don't quite connect, and if they're within 0.001 degree of each other, they'll snap together and get you a node. So with real data, especially like OSM data, when you download it, since people are just typing in their own coordinates, you usually will find a lot of streets and alleys that don't quite intersect, or points that are floating off away from the streets. This will take care of it in one swoop. So you just set the tolerance, and it creates a perfect topology for you. Now, if it finds something wrong with the data that it can't deal with, then it will alert you otherwise. So, for example, if your data doesn't have a source, doesn't have the source or target column already in there, if your geometry column is missing and all that stuff, it will tell you. Okay, so I ran this. It was pretty quick, just six seconds, and on about 5,000 rows of data. Now let's take a look at the flights. So what it basically did is it took the original ID for each of the edges, and it figured out, well, it actually assigned it created another table, and I'll just show that to you quickly. So we started with edges, and this magical function creates another table for you automatically. Called vertices. So this wasn't there before. This table shows you everything by the node. So it creates for each node, so in other words, for each airport, it gave it an ID, and then further, it added the ID to the edge table, both as a source and target. Okay, so now we're ready to do routing. So this is a fully prepared table. We have the minimal necessary. Okay, so I'm going to find out what the nodes are from Raleigh to San Francisco, the site of last year's FOSS 4G NA. Oh, speaking of which, I've been charged to remind you that the FOSS 4G 2017 will be in Boston on August 14th to 18th, and I have a card here to remind you all of that. Okay, so this is, so our Raleigh-Durham is 152, and San Francisco is 32. So we will do our first routing. So dijkstra is the most popular algorithm that is in use for PG routing, and it's basically a formula that will give you the optimal route based on cost. And for this particular query, I'm simply going to say that duration is cost. I want to have the flight that will get me from Raleigh to San Francisco the quickest. Okay, so let me run that. And this is my result. And okay, it's a nonstop flight, which is no surprise. And it tells you which edge it is and what the cost is. It's going to be 320 minutes, which is 5 hours or so. I'm going to substitute in, this is the same query, except I'm going to substitute in RDU and SFO so that I don't have to look up the source and the ID. I should get the same result. Now, for something a little bit more interesting, to show you how to read tables with a few paths rather than just a nonstop flight, I'm going to fly from Roche Harbor to Key West. Roche Harbor is some little seaplane base out there in Washington State. And so this is a more extensive route. So if you want to go from Roche Harbor to Key West, which is UIW, you have to take a seaplane from here to FBS's Friday Harbor, and then finally another little seaplane to Lake Union, and then somehow the seaplane from Lake Union can fly you to Seattle, because I think those seaplanes have wheels underneath. And then you take the big long flight from Seattle to Orlando, and then Orlando to Key West. And this gives you, the sequence tells you 1, 2, 3, 4, 5, so that's your sequence. This is your incremental duration on each of the segments, and then finally your aggregate. So your total is going to be 541 minutes, about quite a bit of time. This is all, not counting in stops and all that. Okay. So another variation of dijkstra is this KSP. So instead of giving you the one best solution, KSP will give you the top N solutions. In this case, I am still going from Raleigh to San Francisco, but I have asked for the top 5 best routing. Let me just... Okay, and in the query, I joined it back to my flights table so I could print out the segments. So this is the top, I'm going to make that down. So this is the top 5, and this is the first one, the second one, the third one, the fourth one, and the fifth one. Okay, the first one is still that nonstop. The second one stops in St. Louis. Is that St. Louis? St. Louis. And then the third one stops in Denver, and then Salt Lake City, and what's CO2? Charlotte. Yeah. Okay. So this is the top 5, and their duration is, you can read that here. So 320 minutes is the shortest still, and then finally you have one that is 75 plus 309. I actually have it added together in this very last column, 384 minutes. All right. Let me show you this on a picture. And I'm using OpenJump here. It's a very quick and easy tool just to visualize your query results. The more sophisticated visualization tool is QGIS, but that has a higher learning curve. Okay, so let me see. Okay, so let me draw in the airports. So those are the airports in the lower 48. Let me draw in the lower 48. That's the lower 48 unprojected lat long, so it looks kind of funny like that. And then this is all the flights, 4,000, or close to 5,000 of them plotted. And then finally, let me show you the route from the top 5 routes from Raleigh to San Francisco. Let me remove the flights so you can see better. So those are the top 5, the 5 shortest in duration routes. Those are the duration numbers from Raleigh, Durham to San Francisco. Okay. Now, and this is the Roche Harbor seaplane route to Key West. Just want to give you a picture. Let me see if I can blow this up and so that you can zoom to select the items so that you can see how let's see if I can blow this up a little bit more so that you can see that there is actually a few stops here in the state of Washington. Let me go back to, okay, let me take that out. And now just for fun, well, not fun, but I set the parameter to give me the top 100,000 optimal path, and then I chose the worst 10, I believe, here. And so this took a while to run. But as you can see, the routing here takes you, to all sorts of bizarre places. And I'm sure there's an infinite number of these if you let it keep going. But this is all I have the patience for. So this is, this is bizarre routing. And again, I don't have prices. If we have prices, maybe that'd be a little bit more interesting. Okay. Okay, let me see. All right, so that's the basic routing where you're trying to find optimal routes between points or the top end routes between points. Now, another use is what's called solving the traveling cells, used to be man, now it's person, traveling cells person problem, the TSP problem. And I'm sure most of you would know what this is about. So the story is that you got a salesperson who needs to visit many cities on his route. And you want to find the path that he should follow, or he or she should follow to minimize the driving or the horseback riding time or distance. So that's the classic traveling salesperson problem. And it's been around since the ancient times, and there are mathematical solutions and different ways of solving it. But you can use pgRouting. So for this example, back here, I got a list of nuclear power plants in the world. Now, this is nothing but Wikipedia. You just go to nuclear power plants, and here comes the data. So there's about 151 nuclear power plants, and the Wikipedia gave me the longitude and the latitude. And let me drop that so I can. Let me drop the geometry column for now. Okay, and so we have 151 plants, including this one, this very famous one. It's still listed in Wikipedia. Okay, so to prepare this data, I'm going to add my usual geometry column. Now this time, I chose SRID of 3035, which is the ETRS 89. Well, this particular one, if you're familiar with National Atlas, that's a common projection that is used in the United States. This one is pretty much the same as the National Atlas, except it's centered in Europe. And why do I center in Europe? And that's because the problem I'm going to have is I'm going to pretend that I'm one of those nuclear power plant inspectors from IAEA, International Atomic Energy Agency. Thank you. And they go around to all the plants and also missile sites around the world to see if everybody is up to standard. So I'm using 3035 because it's better at preserving distance measurements. If I use lat long, I'm not going to be assigning the right cost to things. I mean, if you, because as you know, the latitudes gets, the longitudes gets kind of skinny up at the poles. So that's not going to assign me the right cost. Whereas 3035 is better. I'm sure there are better ones, but this one that looked good to me. All right, so because my data is in lat long, I have to transform it to 3035 using ST transform function. So this is another pretty magical thing that will transform your SRID to any other SRID. Okay. So my 151 rows, and now I have a geometry column that is constrained to be points and 3035. Okay, now, the TSP implemented in pgRouting is nothing more than a function. It's this thing, pgRTSP. It's a function. And the first argument is really just a SQL statement. And it takes the x and the y coordinates of the area that you are trying to optimize over. And then the last two arguments are the starting point and the ending point. IAEA is headquartered in Vienna. There are no nuclear power plants in Austria, so I chose Czechoslovakia. No, Czech Republic, sorry. It's not Czech Republic. So there's a power plant in Czech Republic, which is number 19. And I want to start from there and end there. So that is the setup for the TSP function. And then the second one is simply just so that I can have some pretty names in the output so that you can see. All right, so I'm going to run this function. So this is now the sequence of travel that it will give you the shortest route. You start at Czech Republic, you go through Hungary, you stay around Europe, And then as you go to the UK, and at some point you come to this New Hampshire Seabrook, you play around United States, go to Canada, come back to US, and then, oh yeah, Mexico. And then you go to South America, go over to South Africa, and then you wind up in the subcontinent of India, and then the Far East. And then making our way back through Russia, the Ukraine, and then even Scandinavia. Germany, a little bit more Europe, and you're back at the other nuclear power station that's in the Czech Republic. And let me show that to you in the picture. Okay, so this is the world. Okay, I think I chose this projection because you could see the whole world. All right, and this is the optimal path. Okay, let me see if I can zoom in a little bit. So this is the starting point. This is Czech Republic. There are 2 nuclear power plants. You start at one and you end at the other. And this is the path of traversal. You go through Europe, cross over to the Americas, South America, Africa, and then over to Asia, and back home to IAEA headquarters. That is it for the demo. Does anybody questions? The what? Oh, you mean the color? The behind the scene is exactly, okay, the countries I didn't show you, that's just a table of countries. And in OpenJump, it just selects star from countries in a query. All you have to do is do run database query, create a new layer, select star from country. That's pretty simple. I have a countries table in here. And then the optimal path is simply the optimal path. I calculated that, and I insert it into another table, and then just select from the other table. You can directly put the SQL in OpenJump if you like. The what? The optimal path, let me see. No, it's this. Okay, so it is is this the same one? Yes, it's the same one. I did not cheat.
It would be the same in QGIS as well. I've done the same thing with pgRouting.
Yes, there's also there's a new pgRouting layer. There is a pgRouting layer plugin now that is available, and yeah, it's. Do we know how to answer that?
Like what kind of updates are you looking for? I don't think there were too many updates to the driving policy from what I remember. But was there something specific?
No, I just remember it was a little bit hard to use. I'm wondering if it's any easier.
Driving distance.
Yeah, the driving distance. You're thinking about like applying the alpha shape to the driving distance?
Yeah.
I don't think it's any easier. I think maybe in the pgRouting layer it's gotten easier. That's been combined, but the actual query I still do it as separate, so I do the driving distance, and then they do the alpha shape from that.
Yes.
I noticed with our TSP, you guys did like 150 locations. That means you had to use a heuristic. I was curious what the background and what heuristic you guys, how that's implemented.
No, we do not know. However, there is quite a bit of So Boost is the underlying library, and then you can read about Boost and see what kind of algorithm it used. Anybody else? Okay. If not, that's it. Remember, this book is now 50% off. Okay.